Hello everyone, I am Shiv Prakash. Let's start the session. The given question number first. What is the effect on the response time on increasing proportional gain Kp of a PID controller, keeping integral and derivative gains same? You know about the PID controller. PID controller gain of Kp, Ki, Kd into S. It is given that this one is a constant, only Kp increase. If Kp increase in any control system, any plant, if you Kp increase, then it means the system gain will increase. If gain will increase, the percentage overshoot also increases, and steady state error decreases. If you observe that, I show you by the MATLAB. Take this, but observe that if you Ki and Kd is constant, it means it is inbuilt in the plant system. Only Kp I will take and draw a system like that. If you have a system, again only Kp apply. This one plant. Take this S plus A something. This one Rs input. This one output. Feedback system. If you find transfer function of this, you know GS divided by 1 plus GS HS is equal to 1. GS it means Kp S plus A 1 plus Kp S plus A into 1. And transfer function is Kp divided by S square plus SA plus Kp. If you compare the system from second order standard system, classification of second order, know about S square is 2 zeta omega ns plus omega n square. Yeah, 2 zeta omega ns is the system. Settling time, you know about settling time, 1 by 4 by theta omega n. Here the Kp is not present in zeta omega n. If you look here, zeta omega n is equal to A by 2. It means 4 divided by A by 2. It depending on only A, not a Kp. It means the settle time is not affected by this Kp. Only overshoot gain and P overshoot will increase and steady state error decrease. If you know steady state error, in any system if you take, then find like GS, some I RS is step into 1 by S. Here limit S tend to 0 SRS divided by 1 plus GS. We take RS 1 by S, then 1 by S cancel out. Limit S tend to 0 1 plus GS. If you take a KP like again, then you find KP divided by S plus A. You put a 0 here, then 1 by 1 plus KP. KP by A. If you increase KP, it means like a proportional gain increases, then steady state errors should be decreased, not much more decrease, but some decrease. Steady state error also. And if you increase the gain of KP, then you know about the phase margin. Phase margin will decrease. Phase margin decreases, then overshoot will increase. That's why this one, and I think this one is correct. Settling time not affected. No, this resistance becomes 0. No, because it is not become 0, but some value, some decreases. Same with the question number 2. This one is given. What is the response time in increasing the internal gain Ki? You take a Ki, our PID controller, keeping proportional and derivative same thing apply here. If you know Ki is means Ki by S. Yes, introduce the pole in the system. If you, in your plant, pole introduces pole. If pole increases in the any plant system, then in control system, if pole increases, it means phase margin will decrease. When phase margin will decreases, then over peak overshoot will increase. Any system, if you have pole increases in any system, then phase will be increases in negative. Because the phase of any system is like tan inverse 0 minus tan inverse pole. If pole will increases, then it negative increases, then phi will decrease. The phase margin will increase. So sorry, phase margin will decrease. That's why peak overshoot will increase, and it is settling time. Settling time will increase. No steady error will decrease. This one and this one 0 or decrease. Two options also given here. Same system I will take. I am taking same system like this one, and introduce here Kp. In place of Kp, introduce Ki. Like 1 by K by S. In simple system, you can take any system S plus A. Then total GS Ki divided sorry, S plus A. Steady error is equal to limit tend to 0 S into RS divided by 1 plus GS. Here RS is same I have taken. RS is step response 1 by S. Then this one is 1 plus GS. Here GS is KI divided by S plus A. If you put here 0, that means 1 plus NPT is equal to 0. Static will 0, and if you KI integral introduced in the system, then it is 0 for the step response. So not a decrease, this one is 0. And settling time, because of the integrator, if you integrate if you increase the gain of integrator Ki, then you observe that the system is oscillatory in nature. You will go to oscillatory in oscillator at a point, because of you try to do error 0 in the system. You define as the reference signal and compare to the output signal, and it will try to go for 0. That's why it is oscillate at a point, because of the integrator is the value memory is also there in integrator. That's why previous value compared to the previous value to present value and oscillate at the point. That's why settling time will increase. This option also correct. If you try to observe this, try to solve in the MATLAB system and find what is happening there. If you increase KP, KI, I take a system, a general system, into KID, PID controller used, then P plus KI plus KD. And I will take a plot like system, second order system, AS plus B CS. Here we introduce the RS here and HSC. To find transfer function, you know about the GS divided by 1 plus GS HS. GS is a total function, this one we multiply by this, then we find. I take a common S, then some KD into S square, KP into S plus KI into 1 divided by SQ plus AS square plus BS. S multiply by here, and 1 plus GS, same thing, by SQ. A plus KD to S square, B plus KP Okay. Sorry. I share a screen. Here I have taken A, B and KP, KI, KD value. Starting it like a 10 run the system. Take time. You do the same thing in MATLAB and put the value of KP, KI and KD. And observe the response, step response. Here I will take it as I am increasing the value of Ki, Kp. Then observe what is it. Sorry for that. It did not respond first. Let's connect this. Try to on. This will take more time. And fragment this and do to by yourself. My system not responding. So now I will increase like 10 times. Note down this code in your copy and try to also. This one, what happen if KP, KI will increase and KD also take something. If you increase the KI, then this one our system goes to the steady state is 0. If you increase the KI. I increase the KP, then error will also decrease error, but not as 0 because of if you observe this. This one some error is here, and if I increase KI, 10 times I increase, then you find this is oscillatory system. Certainly time will increase here if you increase the KI. Take a result 20. This one is here it will 0. This is very less. If you take up for more than I will take up 20 seconds, I will take a 30-40 seconds, then it will 0. Oscillatory system, if you take 300 like 400 500 KI will increase and error also decrease. And observe peak overshoot increases here. This one error will decrease, but peak overshoot and oscillatory system will increase. It will certainly time will increase and peak overshoot will increase here. KI increases. Then this one 1.14 would decrease like 200, and then this one so I think something decreases. I'm going for the question number 7. For an ideal buck converter with V in 10 volt and V reference is 2 volt, an inductor and capacitor given, operating with a load feed forward action, the value of proportional gain for time optimal recovery for the step of load change. Step of load change means the load is increased. Load is increasing and delta I is equal to 10 ampere. Okay. This one given for a buck converter. You know for the buck converter circuit, you know very well. This one be V naught CL switch Q. Even the current will decrease. this one graph between output voltage and inductor current. I will take I naught for the buck converter. Average inductor current equal to average output current. We take this point as first point I naught 0 1, and this one the second point, which if you increase I naught something delta I naught. The time optimal recovery, this one, you know, the hysteresis band like inductor current delta H, this one. This one point I could take 0 1 and V0 1. Yeah, this one is reference. We also take and the final value here 0 2. If you increase the load, is a sudden not going to sudden go to this value. We will take some approximation here. Go to here, this one for in going in a band. If you know about the sliding mode control, this one is the sigma plane, going to this in sigma plane, and after that you go to here. If you once you go to in the plane, this one is the control action trajectory, go on the plane. After that, this one value you take like I1 and V1. After that you second time like that here, oscillate like between hysteresis band from the final value. You know about the switching surface sigma, you know, sigma is called like a inductor current minus reference and Kp gain V naught minus V reference. Reference of output reference. What will be say for find the Galois proportional gain, you need to find a Kp value here. For this, first of all, solve this surface sigma is equal to 0. This one is a surface. To take I reference like I naught, the output voltage, output current, and V reference the output voltage, like then we find sigma is equal to IL minus I naught plus Kp V naught minus V. This one the error voltage V naught minus V, or if you take a common negative terms here, then you find I naught minus IL, and you take minus here common, then you find V reference minus V naught. This one is the voltage, error voltage. What we will doing for reference value and what will be our output. And this one IL minus I naught. Here you know this one IL, this one I naught, this one IC. IC is equal to IL minus I naught, but here given the I naught minus IL, it means here minus IC, inductor current, capacitor current, minus Kp into VE equal to 0. So written IC, you can written like C dV not divided by dt is IC, because of same voltage appear here in not. Minus multiply by here, and this one so plus, so for this if you take a reference as 0, and then you find dVE by dt equal to like a minus dV not by dt. Then you can replace V not by itself like V here, minus V, it means C dVE divided by dt Kp into V, take a C common here, take is equal to Kp by C, another constant. This one derivative, you can say this one proportional. Once you add Ki also here integrator, then this one will have dVE divided by dt and some integration also you can add VE dt. So is the PID controller for the buck converter. Now here ask about the load will change from I01 to I02. Then what happened? You know about the average inductor current and average capacitor, average inductor voltage, average capacitor current for the buck converter. You know, if you switch is on, then V in minus V naught will give, it means dV in minus V naught, dV in minus V naught, and when switch is on off, then minus D minus V naught. If you solve this, then you find dV in minus V naught. Same thing you apply for the average capacitor current, then you find IL minus I naught. Then you will take delta IL like x1 you variable take, and V naught take x2. Then find dx2 by dt dx2 by dt means delta IL. This one x2 it means VC also the V0 because of the same voltage VC and V0. VC means the IL minus I0 divided by C. IL is x1 minus I0 divided by C. Same thing if you apply for dx1 by dt. This one, then you find dV in minus V0 divided by L, and dx2 divided by dx1 divided by this function x1 minus I0 by C. L by C, x1 minus I0 to take characteristic equation, root of L by C equal to ZC for I will written calculation, simple calculation, dV in dV in minus x2 dx2 is equal to z square x1 minus I0 dx1. Integrate the both side from initial value to final value, I1 to IF. Sorry, this one is the voltage equation, then V1 to final value, and this one IL, I1 to I. You integrate this and you find two equation IL and I2, and D is equal to on off. You know about the changes. First one I0 here and second one I0, also I0 2 if IL and T taken, then this IL also like that. If you sudden change in I0, then IL also change like that. This one taken I01, this one taken I02. This changes of this I delta I0 output current in buck converter. And this one is the initial value and this one is the final value. But for the sliding mode control, it's not going like that. I1 to I12, I11 to I01 to I12, not going like that. So not going, then sliding mode will go for the certain trajectory touching the surface, and after the I1 V1 I will taken some point. After that go to surface and go to it at hysteresis band and oscillate like that here. The switch is on, switch is off, switch is on, switch off, like that. And this one is the first value, initial value, this one final value for one condition, and this one initial, this one final for the other condition. And switch is on, and this one is the on condition, on trajectory you can say, and this one is the off trajectory you can say. When switch is on, then this one you have initial value to final value, and switch is off, then this one is initial value and this one is the final value. here ZC characteristic equation. To integrate this, you find dv in this one x2 minus x2 square divided by 2 v1 final value. You take initial, you confuse this, bc square x1 divided by 2 minus I naught into x1 I initial to I final. If you solve this, find dv in final minus initial minus v final square divided by 2 minus initial square divided by 2. X final value का square by 2 minus x initial value square divided by 2 minus I naught, x1 is I minus I. We will take this question number 3 something. After this, you use two things. D is equal to 1 for on trajectory and when due to ratio 0 for off trajectory. When due to cycle is 1, it means a high. Then you find this one is on trajectory for D is equal to 1. And find I01 is initial and I1 is final, V01 is initial and V1 is final. Take I01 as initial and I1 as a final and V01 as a initial and V1 as a final value. Same thing apply here. Here initial is a I1 and final is I2 or I not 2 is the final value. For off trajectory, here this one is initial value and this one is a final value. And initial value is V1 and final value V not 2. You know about I not 2. I not 2 is same as I not plus delta I not. That is the final value this one. What is changes in delta I not? We put the value here I1, V1, everything. We will take two equation. This one equation for first, this one to second, and find x1 and I1 and V1 value from this equation. What kind of question is that? here if once we put this one value, and after this one find two equation, and from two equations solve I1 and V1, find I1 value and V1 value. If you solve this, then you find I1 V1. I1 like I01 plus delta I0. I will write directly NPTEL for V in, V reference, in V1, V reference minus delta I0, that's square 2V. Once we find I1 V1, do this. After that, to find a Kp value, we want to find a Kp value. For Kp, sigma is equal to IL minus I reference plus Kp V naught minus V reference is equal to 0. Here I reference take I naught, and I naught for the final value also taken like I naught 1 plus delta I naught. Then this one find like I1, IL put a value I1, and I reference put a value I0. I0 is I0 1 first value plus delta IL, what is change in the current, plus Kp, and V1 find here. V reference is 0. Here so now you find from equation V1 and I1, and I0 1 is given from, and delta I0 also given, what will changes, and V reference is given like output voltage, everything given, only K. Then find value of Kp. From this equation we find value of Kp. To solve this, we find value of Kp like a V in and V reference minus delta I naught square into ZC square divided by delta I naught into ZC square. You know about ZC is under root L by C. Every value is given. Here V in given 10 volt, V reference 2 volt, L 500 nanohenry, C 100 microhenry, and load changes also given 10 ampere. Delta I naught is 10 ampere. Let's see, find from the here L by C. If you solve this, you will find approximately 20.84. This question first for you apply the surface equation for the Kp, because of this one is this slope is minus Kp, and after that find the value of average inductor voltage and average inductor current, and find the slope of this, and after that integrate from initial to final value. We take initial value like that, initial final on trajectory. If off trajectory, take this one to this one initial, this one final. Sometimes solve for I1 V1 value. Once I1 V1 you find, after that you solve, put the value in the surface, switching surface. Okay, if you find from there. Question number 4 is given. For an ideal boost converter with a 5 volt input, V reference 8 volt, inductor and capacitor given, operating with a load feed forward action, the value of proportional gain, same thing apply for this. Recovery 5 step down operation, load changes from 5 to 2 ampere. It means delta I naught is equal to 3 ampere. Same thing apply for boost converter also. I have written directly Kp value here. Kp approximately C by L and by V naught by I naught. I naught, what will change I naught? This one is a 2 ampere, from 5 to 2 ampere. All value is given. Simply apply, approximately I think 25 will give. Same trajectory you will use. Time V naught and IL, and then the 2 point, this one V reference, this will not change because of output voltage. This one is I naught 1, this one I naught 2 or IL. Change from here to here, once trajectory given, so or given, go for here, after that go here. So 2 point, this one take a V reference and I1, and here take a V1 I1, here take a V reference same and I naught or output voltage, output current. Same process apply and find the value of Kp. What is the correct surface for optimal step of recovery in an ideal buck converter? This one same I have written here. IL minus I reference, V naught minus V reference, Kp. I think C option. IL we take common here. This one ISO number A is correct. V reference minus V naught, I reference minus I naught. So Kp apply for the output voltage. Question number 6 is given. Which of the following is true in case of dynamic power in mobile processor? If you know dynamic power in mobile processor, dynamic power is like omega C into V square, VDD square is what? V square by X. Then this dynamic power directly proportional to VDD square and to omega proportional to frequency. Both are directly proportional. VDD not VDD square, inversely proportional, no, directly proportional, yes. An ideal PID controller implementation is possible using analog control. Analog control not possible because of an analog control you use op-amp. Op-amp have some bandwidth limitation because of and you know about PID controller. Proportional gain is okay, and the integrator also okay, but derivative, when you derivate the system, derivate the noise, then high frequency noise will come in the system, and op-amp may have some limitation or the bandwidth or frequency. That's why you want to use the ideal PID controller. For the PID controller, you use a practical PID controller and use a filter and derivative system. And magnitude of the noise also increase if you take in PID controller. You know, so Kp plus Ki Kd into S. Now if you have a noise system like a step response, if you integrate of this system at edges, this one is the impulse system. This impulse system, this one is very high impulse attack on the system. That's why you use a practical system like Kp plus Ki plus Kd into L. On a filter we will use TTS. This one is the low pass filter. And this is the frequency of this one TD, time constant, depending on the noise or what the frequency of the noise. That's why this one is not true, this one is false. If you use a practical PID controller is possible using an analog control system. This was, I think, this one last question. I'm stopping here. This video also uploaded on YouTube. Okay, thanks to everyone.